Below this, in the outer parts of the lower mantle, you can see a transition zone where the rocks become denser. Some examples of such rocks are olivine, peridotite, and ringwoodite. These high-pressure minerals form within the mantle, and as you can see, they look beautiful. Now, if these minerals are found inside the mantle, how do we extract them and see them? Actually, we didn't take them out. Nature, our Earth, brings them out. Sometimes when there are volcanic eruptions, the magma that erupts from the volcano carries these high-pressure minerals from the mantle. Or sometimes, when a meteorite hits and falls to Earth, it crashes at such a speed that this pressure is enough to form such minerals. Moving inward, we get to the inner core. In the inner core, iron continues to stir due to the heat, which creates electric currents. Since iron is a good conductor of electricity, these electric currents then form a magnetic field. This magnetic field is one of the main reasons Earth can support life. It is this magnetic field that provides protection against the harmful charged particles emitted by the sun. It shields us from solar winds and helps keep the atmosphere intact. The biggest difference between the outer and inner core layers is that the outer core is in a fluid state, while the inner core is solid. Interestingly, as the fluid in the outer core cools off, it is solidifying. This is why the inner core layer increases by about 1 millimeter every year. Now, another question in this story is, how was the moon formed? The Earth was formed, but how did Earth get its moon? Friends, the answer lies in the Hadean age. Scientists have proposed many theories about how and why we have the moon. One of them was the capture hypothesis, which suggested that it was a planetary object that came near Earth and was captured by Earth's gravitational pull. This is known as the capture hypothesis. Another theory was the co-formation hypothesis, which suggested that the moon and Earth formed simultaneously. When Earth was forming, pieces and bits of dust particles were coming together, and the moon was forming in much the same way. Another theory is the fission hypothesis, where a piece of Earth broke off and turned into the moon. However, do you know what? These theories were all false. Today, most scientists believe that another planet collided with Earth, and this collision led to the formation of the moon. This theory is known as the giant impact hypothesis. According to this, about 4.5 billion years ago, while Earth was forming, there was another protoplanet, which has been named Theia. It was about the size of Mars. Around 100 million years after the nearby planetesimal group was formed, this planet collided with Earth. At this point, Earth was just a mass of magma, and so was this planet. What happens with this impact is that the centers of both planets combine into one. Meanwhile, a huge chunk breaks off, which later becomes the moon. 30% of Earth's total mass is due to its iron-rich core. But for the moon's case, it makes up just 1.6% to 1.8%. This means that most of the metals from this other protoplanet stayed on Earth and became part of our planet, while the moon came from the debris of this impact. Are you wondering how we can be completely sure of this? Actually, when NASA sent the Apollo missions to the moon for the first time, they brought back soil from the moon. The examples of basaltic rocks tracked down in the moon's mantle were basically the same as the basaltic rocks tracked down on Earth. The oxygen isotopes and different components tracked down in the moon's stones were very like those tracked down in rocks on Earth. Thus, according to this point of view, of the three dismissed speculations, the partition hypothesis was the nearest to reality. The moon was really a piece of the Earth. However, it wasn't like the Earth fell to pieces all alone and the moon tumbled off. A piece of Earth fell to pieces just when another planet slammed into it horrendously. On the screen, you can see a reenactment of this event made by NASA's supercomputer. In any case, do you know what's astonishing? Without this crash, we wouldn't be alive today. This crash had an enormous effect on Earth's rotation. This caused the 23.5 degrees rotational tilt. Without this rotational tilt, we could never have seen seasons change from summers to winters and back to summers. The climatic variations would have been so severe that it would have been incredibly challenging to adjust to life. Furthermore, Without the moon, there would be no maritime tides. These variations, known as low tides and high tides, assisted living creatures with moving from the seas to land, returning to the Earth in the Archean Age. There were many other developments that allowed life a chance to start. After the separation of the three main layers, things began to stabilize. There was a lot of volcanic activity. Volcanoes erupted, releasing a lot of gases like water vapor, carbon dioxide, methane, and ammonia into the atmosphere. This is actually a poisonous combination of gases since it desperately lacks oxygen. However, over time, as the Earth slowly became colder, water vapor began to gather. This dense water vapor started to condense and fall upon the Earth. What's more, following millions of years, we had these gigantic seas on Earth's surface. I have already mentioned another reason for the formation of seas in a previous video, the impact of the constant bombardment of asteroids and comets. This liquid water was present in enormous amounts and played a vital role in life on Earth. It absorbed most of the carbon dioxide and heat from our air. As a result, on Earth's surface, temperatures became sufficiently comfortable, and the oxygen levels began to rise. Do you know what's astonishing, friends? Even today, the fossil fuel byproducts, the carbon dioxide produced by human activities, are mostly absorbed by our seas. Many people believe that forests and trees contribute the most. However, it isn't the case. The seas are the ones doing most of the cleanup. Unfortunately, the sea's capacity is gradually reaching its limit. This is an interesting topic, and I can make a separate video on it if you want me to. Comment below if you like that. For the time being, I would like to end this video now. The events I discussed in this video were the preconditions. Had things not happened this way, perhaps life would not have had the opportunity to proliferate. The sun being at the perfect distance from Earth, neither too far nor too close. Earth's size being the perfect extent, neither too large nor too small, for the gravitational pull to work correctly, maintaining the right components in the air. This kept exactly the right gases in the atmosphere that support life. Third, having a magnetic field at Earth's center of the perfect strength, a magnetic field that protects us from the hazardous gamma rays and X-rays produced by the sun. Fourth, having exactly the right amount of volcanic emissions, which gave rise to just the right amount of the greenhouse effect. Had the greenhouse effect been too extreme, there'd have been a higher carbon dioxide concentration and lower oxygen levels, similar to Venus. However, had the greenhouse effect been weaker, Earth's climate would have been like Mars. It would have been too cold, unable to maintain a strong atmosphere, and would not have had sufficient amounts of liquid water. Some comets and asteroids that crashed into Earth contained high concentrations of water. You might wonder how those asteroids and comets got water. Friends, that was due to the solar nebula. The dust cloud I mentioned earlier in the video contained ice crystals as well. Indeed, even our Earth had some water. When the minerals trapped inside the microscopic crystals from the Hadean Age period were dissolved, it was found that liquid water was present on Earth as well. But the rising water on Earth was caused by the impacting asteroids and comets. In the process, another interaction was happening. During these impacts with Earth, the water would turn into steam and rise up. Over time, it would come down as rain. By the end of the Hadean Age, our Earth had turned into a homogeneous ball. There was magma everywhere. The Earth had become nearly like a uniform layer of magma, held together by gravity. This led us to differentiation. Once again, you might wonder, how could we be sure these events happened back then? Friends, the discoveries are supported by various methods. One of them is radiometric dating of rocks, studying billions of years old minerals to check their composition. Another method is planetary geology, looking at the composition of different planets to understand what they were like in recent history and how they developed. And the third is running virtual experiments. The gases and elements present back then are taken as inputs for the program. The model runs based on this data, and scientists then monitor the model's behavior. This is how data science was used to better understand our planet's history. It is used in almost every industry. automotive, finance, media, healthcare, etc. If you want to upskill yourself in this field, or if you want to enter this exciting field, then the sponsors of this video, Scalar.com, have a solution for you. Scalar is an online tech learning platform. It offers programs in software development, data science, and machine learning. Industry experts from top tech companies mentor students. Scalar has helped more than 15,000 people in their career transition. You can see the success stories of students in this section. Students get access to over 100 capstone projects, which help them become industry ready. Scalar has partnered with more than 900 companies, including Google, Meta, Flipkart, Amazon, Myntra. Through this, they give work assistance to their students. They offer a simple EMI Choice 2 for a considerable length of time at 0% interest. Assuming you feel that Scalar can assist with supporting your career, utilize the link to their website given in the description. You can use the link to pursue a free live masterclass. They offer masterclasses on different themes. It will assist you with making a decision about the value of their programs. What's more now, let's return to our topic. Today, we all have some familiarity with Earth's three principal layers: the crust, mantle, and core. Toward the Hadean Age's end, Earth's outer layer had already begun to form. However, the separation of these three layers occurred during the next period, the Archean Age. The word Archean comes from the Greek word arche, which means beginning. So, from this period, essentially, Earth began to take shape. This period lasted from about 4 billion years ago to 2.5 billion years ago. During this period, the massive magma, which was our Earth, contained various elements in it. The heavy elements, like iron and nickel, because they were denser than other elements, continuously started flowing into the magma and began accumulating at its center. It's similar to how water flows through sand. The simple explanation for this was the force of gravity. The heavier elements, iron and nickel, continued to be pulled toward the center, while the lighter elements, like silicon, oxygen, aluminum, sodium, calcium, and potassium, began flowing upwards toward the surface. The flow of the different elements towards the center or the surface continued to accelerate with time, and gradually, at the center of the Earth, the core began to take shape. When iron and nickel began merging, we know that Earth's core is its hottest part. The temperature reaches up to 6,000 degrees Celsius. Naturally, iron would melt at this temperature. However, the pressure at Earth's center is so high that iron doesn't melt at this temperature. Instead, iron and nickel are present in the Earth's core in their solid form. Today is the same, and the reason for this high temperature is not only the high pressure and gravitational force, but also the constant radioactive decay in the mantle layer. Elements like uranium, thorium, and potassium lie in the mantle layer. They are undergoing constant radioactive decay, and this is a significant source of heat for Earth. The mantle is the thickest layer. It is more than 3,000 kilometers thick. Today, this layer is solid. However, back then, this layer was not solid. It was filled with magma. When the lighter elements were flowing upwards, they cooled at the surface. Thus the outermost layer, the crust, was formed. Oxygen was the most abundant element in this crust. 46% of the crust's mass was made of oxygen. If we delve into the details of these elements, we could have an extended discussion. The different types of rocks found on the surface today, like granite and basalt, and metamorphic rocks found in the deeper layers of the crust, like marble or slate, show a clear transition as you move outward from the mantle toward the outer layer. Since rocks like marble and slate form due to very high pressure and temperature, that's why they are found only in the deep layers of the crust. And if more heat and pressure are applied to them, they revert back into magma. Apart from this, there are sedimentary rocks in the upper layers, like sandstone. These rocks were in a constant cycle of development and breaking down due to weathering, since they were exposed to sunlight, air, water, and snow. Coal is also considered a sedimentary rock. It is a type of sedimentary rock that has undergone both chemical and physical reactions. So, in general, this separation process continued for millions of years. during which the layers of our Earth were formed. Students are often taught only about the layers: crust, mantle, and core. However, there can be many more divisions in the layers. If you study geology in detail, you will find that Earth is divided into not 3, but 5 layers based on their physical properties. These layers are the lithosphere, asthenosphere, mesospheric mantle, outer core, and inner core. The lithosphere is the outermost layer. It is divided into 2 parts, oceanic and continental. The crust under the seas and the crust under the continents are essentially different. The crust under the seas is much thinner, with an average thickness of about 100 kilometers. But the crust under the continents can be up to 280 kilometers thick. This is where we come to the tectonic plates. Since this is not a continuous layer, it is made up of many parts, in fact. The areas where the edges of these plates meet result in volcanoes. When they rub against each other, it causes earthquakes. The layer beneath it, the asthenosphere, is not rigid. It moves continuously and behaves like a lubricant. The word astheno means weak in Greek. Unlike the lithosphere, this layer is continuous. It doesn't have parts or pieces. Its average thickness is around 140 kilometers. Hi, companions. Could you at any point imagine this world on which we humans have been born? This world which is home to innumerable types of living creatures. This very Earth was a chunk of bubbling magma quite a while back, a ball with no sign of something going on under the surface. This asks the obvious question: how did this wad of magma change into the Earth we live in today? Where did water come from? How was the moon formed? These are all connected to the birth of our sun and solar system. In this video, let's figure these out in depth. Around 4.6 billion years ago, that is, 4,600,000,000 years ago, there was no such thing as our solar system. All that existed was darkness, deep, silent, and empty space. In this space was a cloud full of dust and gas. This cloud is now known as the solar nebula. In Hindi, it is called Niharika. It contained various gases, with hydrogen and helium being the most abundant. This cloud was calmly moving through the darkness of space for a long period. Then, suddenly, at some point, there was a major explosion. And no, I don't mean the Big Bang. I'm talking about a supernova. This blast wasn't caused inside the cloud. It happened somewhere near it. A dying star exploded near it. This type of explosion is known as a supernova and often happens to stars that reach the end of their life. The shock waves of this explosion reached our solar nebula and caused gravitational instability. In certain regions of this cloud, the gas and dust began to compress. Gradually, the entire cloud started imploding inward, and the gas and dust began spinning around it. Now, the cloud looked like a spinning disk. This flat, rotating disk is known as the protoplanetary disk. Proto means before. The disk existed before the planets were formed. As shown in the animation on the screen, this was what the disk looked like. Since this disk was flat, it helps us understand why our solar system is flat. I discussed this in the Explorer video. When the planets of our solar system orbit the sun, they are almost on the same plane. The orbits of the planets aren't significantly higher or lower than each other. Now, at the center of this protoplanetary disk, the pressure and temperature continued to increase, giving rise to a protostar. Protostar essentially means before a star was formed. Gradually, the objects in the cloud were pulled toward the center due to increasing temperature and pressure. At one point, the center became so dense that nuclear fusion reactions began. Hydrogen fusion started at around 15 million degrees Celsius. In this reaction, hydrogen turns into helium. Thanks to this fusion reaction, our sun was born. This reaction is still occurring on the sun and is the source of sunlight, heat, and light on Earth. The details of the actual reaction are quite complex. However, in general, hydrogen is being converted into helium. Back then, 4.6 billion years ago, most of the gas and dust in our solar nebula was combining into the sun. This is why even today, The Sun makes up around 99.8% of the total mass of our solar system. The remaining 0.2% didn't go unused. That 0.2% represents 8 planets, many moons, countless comets, and millions of asteroids in our solar system. However, the question is, how did these planets begin forming? That's so fascinating. Small dust particles in the rotating protoplanetary disk began colliding and sticking to each other. This happened due to static or chemical binding forces. Initially, they formed into small clumps. Over time, the clumps began growing larger as more dust particles collided with them. Gradually, some of them got so large that their diameter went from 1,000 meters to a few kilometers. These bodies are called planetesimals, a tiny version of planets. When gravity organized these planetesimals and their mass or size became as large as our moons, they were called protoplanets. The process of these dust particles coming together is known as accretion. Take a look at how accretion is defined in cosmology. The coming together and sticking of matter under the influence of gravitational forces to form larger bodies. The accumulation of materials leads to the formation of larger bodies. This process of accretion was introduced to the world by Soviet Union cosmologist Viktor Safonov in 1969. However, back then, nobody took him seriously. It was only in 1984 that Safonov's work began to be examined, and his ideas were adopted by established scientists. Today, researchers have observed this process of gradual accumulation throughout the universe using powerful telescopes. Cosmologists have seen this event in other stellar nebulae, where dust particles accumulate rapidly, and in just a few thousand years, they grow to about 1 centimeter. Since this has been observed in various stages, scientists can now confidently say that for millions of years, these small particles continued to grow and eventually became planets. Another piece of evidence for this process can be seen in meteorites. When scientists study the meteors that fall on Earth to analyze their chemical composition, something that has been found repeatedly is chondrules, small bits of dust and rocks from the time before the planets formed. They contain radioactive elements like uranium and hafnium, which help researchers figure out the age of these bodies. Interestingly, another fascinating fact is that the uranium found on Earth is older than our solar system, believed to be 6 billion years old. This means that it was formed in some supernova. By collecting data from these measurements, scientists can create simulations of the impacts of dust and planetesimals. These simulations help us estimate that it would have taken millions of years for the protoplanets to form. Now, let's talk about our Earth. These small protoplanets and planetesimals frequently collided with each other. These weren't small bumps. They generated a lot of energy. These generated so much heat that they melted rocks, resulting in oceans of magma. As these protoplanets collided with each other, they grew. Due to gravity over time, they began to become spherical in shape. After various such impacts, our Earth was born. Over millions of years, gravity organizes these stones to form the Earth, one of at least 100 planets orbiting the Sun. During this time of constant collisions, small protoplanets or planetesimals would often crash into our Earth. This period is known as a Hadean age. The word age means a very significant period, and the name Hadean is derived from the Greek god of the underworld Gehenna. I guess you can already see why they chose this name. Back then, Earth was much like the way hell is described. This was a period between 4.6 billion years ago to 4 billion years ago. Some objects that crashed into Earth during this period were as large as 100 or even 200 kilometers in diameter. Any rocks that existed on Earth at that time would melt and turn into magma. The Earth kept compacting repeatedly. But now comes the most amazing part. This dreadful age was the reason we have water on Earth. So, friends, you should appreciate one thing from all of this. Everything that occurred was extraordinarily remarkable, and that's why it should be all of our responsibility to protect this superb planet. For all these things to occur correctly is so rare that perhaps that's why we haven't found extraterrestrial life yet. Scalar's link is given in the description below. Friends, if you like this video, you'll like this one as well. In it, I discuss evolution on Earth. How did humans evolve? Which creatures are we closely related to? Click here to watch it. Thank you kindly.